Hi, imagine this. You have just launched your API gateway on AWS. Traffic starts climbing. You get more and more clients as your project gets more and more popular. Then your API gateway starts returning 502s. Your DynamoDB writes are failing and you wake up with tons of alerts in your mailbox. Was that a rate limit? Was that throttling? Does the difference actually matter? Yes, it does. And if you don't know which one you're dealing with, you're going to fix the wrong thing. In this video, we're going to cover what rate limiting and throttling actually mean, the real conceptual difference, and then we're going to look at two AWS architectures where this plays out in practice. By the end, you'll be able to look at any distributed system and immediately identify where rate limiting belongs, where throttling kicks in, and how to design around both. Let's get into it. In the beginning, let's start with theory and figure out what are rate limiting and throttling and what they actually mean. Rate limiting is a policy. It's a deliberate rule you put in place at the boundary of your system to control how much traffic any given client is allowed to send. In technical terms, rate limiting caps the number of requests a client identified by an API key or an IP address or user ID can make within a time window. Hit the limit, you get back 429 response code, too many requests. The system is healthy, the system has capacity, it's just not available to you right now. Rate limiting is typically enforced at the entry point of your system. It is an intentional design decision. The reasons you do it are fairness between clients, preventing abuse, enforcing pricing tiers, and protecting downstream systems from a single actor monopolizing your capacity. On your screens, you can see a token bucket algorithm is one of the algorithms that are used to implement rate limiting, and we can define different parameters like how much tokens we have and how quickly our bucket refilled, and the bucket defines the threshold of how many requests we can see. If we send too many requests, we deplete our daily quota, and at the end you can see that we get a lot of 4 to 9 too many requests errors. Throttling is different. Throttling is a response, not a rule. It's what your system does when it's approaching the limits of what it can actually handle, regardless of who is asking. In technical terms, throttling is your system protecting itself. When Lambda concurrency is maxed out, when your DynamoDB table is out of write capacity units, when Kinesis shards are saturated, the system starts pushing back. Sometimes it queues, sometimes it drops, sometimes it surfaces as an error, but the intent is self-preservation and graceful degradation. AWS is interesting because it uses the word throttling everywhere. But it's doing both things, depending on which service and which layer you're looking at. Let's break it down quickly before we get into architectural diagrams. And the first service that we're going to look at is API Gateway. API Gateway does both things, rate limiting and account level throttling. On one side, it has usage plans and API keys, that's rate limiting. You defined a quota per key per day and rate limit in requests per second. That's a policy you're enforcing on your clients. On the other side, API Gateway has account level and stage level throttling limits. That's the system protecting itself. Your account has original default of 10,000 requests per second, and if you hit it, everything across all your APIs in that region starts getting throttled. Lambda throttles based on concurrency. Every account has a concurrency limit, by default 1000 concurrent executions in most regions. When you hit that, new advocations either get throttled immediately for synchronous calls or queued and retried for asynchronous ones. You can also get reserved concurrency on individual functions, which caps how much of that pool a single function can use. That's a design tool we'll use in this architecture. DynamoDB enforces throughput in terms of read and write capacity units. With provisioned capacity, if you exceed your allocated write capacity units, read capacity units, you get a throughput exceed exception. On-demand mode is more forgiving about that, but has its own soft limits. Kinesis throttles at the shard level. Each shard can handle 1 MB per second of writes and 2 MB per second of reads. Exceed that, you get throttling errors. The number of shards you provision is your throughput design decision. One important note: AWS distinguishes between service quotas, hard limits on your account you can sometimes raise, and configuration limits you set yourself and architectural limits baked into the service. Understanding which one is hitting you determines whether you need to file a quota increase, change your configuration, or redesign the architecture. Okay, let's look at the first architecture. This is a classic serverless REST API pattern. Client applications hit API gateway, which runs Lambda Authorizer to validate the token, then routes to business logic Lambda, which reads and writes from DynamoDB. Let's walk through every layer where rate limiting and throttling can occur. On the API gateway, usage plan and API keys are primary limiting layer. We have attached API keys to our clients, maybe different tiers, maybe per tenant. Our usage plan defines this key gets 1000 requests per day and no more than 50 requests per second. If client exceeds that, they get a 4 to 9 error back immediately. The request never even reaches our Lambda function. This is intentional and this is good. We are enforcing a business policy at the edge. Another measure here is stage throttling. API gateway can use stage throttling separate from usage plans. Every API gateway has a burst limit and a rate limit. The burst limit is how many requests can be served simultaneously from the token bucket. Default is 5000. If the traffic across all clients, all API keys exceeds this, API gateway throttles at the stage level. This is the system protecting itself. We can tune this per method if you want to isolate high traffic routes. Next layer is Lambda Authorizer. Here's one point people often overlook. Your Lambda Authorizer is itself a Lambda function. It's subject to the same concurrency limits. If your API traffic spikes and the authorizer gets overwhelmed, you'll see throttling here before your business logic even runs. The fix here is to enable authorizer caching. API gateway can cache the authorizer's response for a given token for between 0 and 3600 seconds. Set a reasonable TTL. 300 seconds is common, and the vast majority of requests won't invoke the authorizer at all. This is both a latency win and throttle prevention strategy. And layer 4 is business logic Lambda and reserved concurrency. You should set reserved concurrency here deliberately. Reserved concurrency does two things. It guarantees that the function always has capacity, those units are reserved for it, and caps how much of the regional concurrency pool it can consume. So a traffic spike on this one function can't starve your other functions. Think of reserved concurrency as both a floor and a ceiling. Set it based on your expected peak with some headroom and test what happens when you exceed it. And finally, layer 5 is DynamoDB. DynamoDB is at the bottom of the stack. If we are on provisions capacity, we define write capacity units and read capacity units. A burst of writes that exceeds our provisioned write capacity units will get throttled. The SDK will retry, but eventually surface an error if it persists. On-demand mode in DynamoDB absorbs more variation but has its own doubling rate limit. Now let's look at a fundamentally different challenge, IoT ingestion. You've got potentially thousands of devices, sensors, cameras, industrial equipment, all pushing data continuously. The traffic profile here is completely different from a human-driven API. Devices don't back off gracefully, and they don't read your documentation, they just send. This architecture uses API gateway to ingestion front door, Kinesis data streams as their buffer, and Lambda as the stream consumer that processes batches from Kinesis data stream and stores the data to the storage layer, in our case S3 in DynamoDB. Why this architecture is different? In the REST API pattern, a human or application is on the other end, and you can return a 4 to 9 error, and the client is supposed to back off. Here, a firmware device may not handle a 4 to 9 status code gracefully at all. It might just drop the reading, or it might hammer you harder. You can't always control the client. So the architecture itself has to absorb the load. On layer 1, we have API gateway as their ingestion front door. API gateway here isn't enforcing per device rate limits. That would be operationally painful with thousands of devices. Instead, it's acting as a managed HTTPS endpoint that handles TLS termination, basic authentication, and forwards those events into Kinesis data stream via direct integration. The API gateway throttle limits here act as a last resort safety valve to prevent Kinesis from being overwhelmed at the HTTP layer. On layer 2, we have Kinesis data streams as the buffer. This is the key design. Kinesis is the throttle mechanism. Instead of refusing excess traffic, you absorb it into the stream and process it in controlled rate downstream. Kinesis data stream consists of one or more shards. Each Kinesis shard handles 1 megabyte per second of incoming writes and up to 1000 put requests per second. And the shard count here is the primary throughput design decision. If we have 500 devices, each sending 2 kilobytes every second, that's 1 megabyte per second, one shard. If we scale to 2000 devices, we need at least 2 shards. So that is a design choice we must make depending on the number of devices. On layer 3, we have Lambda batch consumer. Lambda function reads from Kinesis in batches. We control how aggressively it consumes via 2 knobs: batch size, how many records per invocation, up to 10,000, and parallelization factor, how many concurrent Lambda invocations per shard, between 1 and 10. That is our processing throttle. We need to tune it based on how fast our downstream storage can absorb writes. If we set batch size to high and parallelization factor to high, we'll overwhelm our storage layer, and we will have throughput exceeds on write capacity units in DynamoDB or throughput exceeds on S3. And the whole design philosophy here is different from the REST API. In REST API, pattern throttling is something that we want to prevent and handle gracefully. And here in the IoT pattern, we are embracing the throttle. We are designing Kinesis as a managed buffer, so throttling never surfaces to devices in the first place. The stream is the shock absorber. So, rate limiting is a policy at the gate. It controls who gets access and how much. It's intentional, it's client-facing, and it's how you enforce fairness and monetization. Throttling is capacity managed inside the system. It's the system protecting itself when it's under pressure. It's about stability and graceful degradation. In AWS, this line blurs. The word throttling gets used for both rate limiting and throttling. What matters here is understanding which layer is limiting and know why. Design your system so that rate limiting at the edge prevents throttling deeper in the stack. When throttling does happen, and it will, make sure it fails clearly, retries intelligently, and surfaces the right information to the right people. The architecture we walked through today, the REST API pipeline and the IoT ingestion pipeline, represent two very different philosophies. One fights the spike, the other absorbs it. Know which approach fits your workload and design accordingly. If this was helpful, like and subscribe. More system design and AWS architecture content coming. See you in the next one.